Hi there, this is the second video clip in which I'm going to look at how you separate the components of a mixture. The principle is based on that the components have some difference in their properties. Maybe one's got a low boiling point, a high boiling point. They've got differences in their boiling points, differences in their solubility, etc. So imagine I've got a simple example, water and sand. I use the technique of filtration. Here's my filter funnel. I put inside it a piece of filter paper and I add my mixture of sand and water to that in the top. The water drips through, collect it in a beaker, and the sand remains in there. So one is soluble, one is insoluble, a difference. Let's look now, how would I separate the components of salty water, i.e. just salt in water, mix it up and it dissolves. So now I've got a solution of salt, saline water. That's simply done by evaporation, and sometimes it's called crystallization. So I take an evaporating dish, a gauze, a tripod, heat it with a Bunsen burner or an electrical source of heat I could use, pour it into that, heat it up, the water evaporates, comes off in the form of steam, and I'm left behind in a basin white sodium chloride, a solid. That is the principle of evaporation, sometimes called crystallization. Let's look at a second example. I've made a solution of copper sulfate, which is blue, stick it into a beaker, add water, mix it up, and I've got a blue solution of copper sulfate. Exactly the same again, evaporation basin, gauze, heat it up. Here's the solution of my copper sulfate, heat it up. The water turns to steam and comes off, and I'm left behind there with blue copper sulfate crystals. You got to be careful, because if you heat it too much, the crystals contain they contain water, and if I heat it too much, the water part of the crystals, called water of crystallization, comes off again in the form of steam, and I'm left with white anhydrous copper sulfate. And of course, if I then tipped water back into those white anhydrous copper sulfate powder, it would turn back to blue hydrated copper sulfate. So that was the concept of crystallization. The third method relies again on some difference in the physical properties, and let's look how I would separate again salt from a salt water solution, but this time I want to collect the water that comes off the steam. I want to collect it. What I do is I have a simple distillation flask. So here is a thermometer, and here's a bung. Right, so I've put the thermometer at that position on the neck on that flask. There's my salt solution, and here is what I'm going to put on there is a cooling jacket. If you like, just cold water goes in and comes out there. So this is what happens. I heat my salt water solution, the water comes off, and if I've watched that at 100 degrees centigrade, the water comes off in the form of steam. It goes down there. You've got that cold jacket, a Liebig condenser. The water cools it down, so that part of that tube is cooled down, and out of the bottom comes water, and you're left behind in the flask with your salt. The same technique can be used to separate two liquids, and this is sometimes called fractional distillation because it relies on the difference in the boiling point of the constituents of the mixture. For example, imagine this is now a mixture of ethanol, ethyl alcohol and water. It's a clear solution, a mixture of ethanol and water. There it is. I heat it up to just 78 degrees. What happens is the ethyl alcohol, the ethanol, boils at 78, water boils at 100, so if I warm that up to just 100, if I heat it just to 78 degrees centigrade, the ethanol, the vapour, comes off. It's cooled down when it hits that condenser here. It cools it down. The vapour condenses to form ethanol again, which just strips out, and I'm left there with water. It's sometimes called fractional distillation. A commercial example is this: black tea, Texas Gold, oil comes out the ground, and it is a complex mixture. It contains solids, liquids and gases, and in simple terms, the lower gases are boiled off at first, followed by the liquids, the petrols, the liquid part, and you're left in your flask or in your distillation, fractional distillation vessel. You're left with the bitumens, tars, etc. But I'll be talking more about cracking of oil, fractionation of oil, etc. And the final technique is chromatography. Chromatography is used to separate mixtures. For example, if you see that pen, it contains an ink. That ink contains a number of different pigments, i.e. black ink is probably composed of 5 or 6 different pigments. I'm about excuse me, to sneeze. Let's look at paper chromatography. Chroma, by the way, chromos from the Greek meaning colour. So if I took a piece of paper, chromatography paper, and I draw a pencil line, very light one, and then I put one of that pen, and I make a dot of it, and then if I had something like that's black ink, and if I put red ink, like that, or maybe green, and I place it into a vessel, as you were, into a vessel that contains water, but I'm filling that up now just to beneath that baseline. What happens is the solvent, the water, comes up to the chromatography paper, and by capillary action it advances up. As it advances up, it will separate the black ink into a series of different constituents. These may be a little bit of red and blue and green, etc. And it works on the principle that different components have different solubilities. The special word is they have different partition coefficients. So the water, like I've said, comes up here, and suppose it's advanced that far. We've got a value called the RF value. It's sometimes called the retention factor, and it's equal to the distance that the solute travels divided by the distance the solvent, i.e. if I wanted to calculate the RF value of that spot, it would be that distance divided by the distance the solvent front. And that is the concept of paper chromatography. And as I've said, when I first started to talk about this module, it's because of the difference in some properties of the constituent components of the mixture. I'll be expanding on this in a later module.